All right, in this work example, we're looking at the question, the diagram shows a man standing on a platform that is attached to a flexible pipe. Water is pumped through the pipe so that the man and platform remain at a constant height. So we're not changing our height. There's a little diagram there showing that. It says the resultant vertical force on the platform is 0. That's really critical, right? So this is like a Newton's second law. The sum of the forces is 0. The acceleration is 0, right? The sum of the forces is 0, so the down's got to equal the ups here. The combined mass of the man and platform is given, 96 kilograms. The mass of water that is discharged vertically downwards from the platform each second is 40 kilograms, so 40 kilograms per second. All right, so the very first thing that I would do here is calculate the weight of the platform and man. So I'll sort of, draw it over here. So the man and platform have a combined mass of 96, and here on Earth, G is 9.81. And so let's calculate the 96 kilograms times 9.81 newtons per kilogram. Give us a total weight of 942, thereabouts. 941.76 is the calculator value, right? Kilograms cancel, that's newtons of force. If the resultant force is 0, and we know that weight always goes down, there's got to be an up force equal to that. So we're looking for a force that is also 941.76 newtons, okay? If we think about force as mass times acceleration, but we know that acceleration is like velocity divided by time. It's kind of just like, oh, well, look, they've told us what the mass per time is, right? They've given us the flow rate. So it's kind of like mathematically, we could just kind of rewrite this like, well, mass over time times velocity then would give us the force over here, the 941.76 newtons we know we need to balance the weight of this person. So then you just plug in 40 kilograms per second, right? That's the flow rate. What's the velocity that's required for this 40 kilograms per second of, water flowing out to give us enough thrust, upward force, to equal that? Well, my headache is getting worse and worse. Literally, I can hear my brain counting right now, you guys. It's getting really bad. This would be the last one for the day sometime. It's like somebody's hammering in my brain right now. I can hear it. All right, so we're going to divide each side by 40. And we get 23.5. Okay, 23.5 meters per second. It's close enough to 24 meters per second that we could choose choice C. The units are such a big clue in solving this, okay? If we know that newtons of force are kilogram meters per second squared, and then we look at oh, well, what units are we given over here? We got kilograms per second, right? We're just missing meters per second of velocity to multiply by that to get newtons of force, right? We need, it's the same idea of basing. It's like homogeneity in the equation. We need newtons on both sides of this, right? And so writing the units out, again, is a big clue in solving it. So when we multiply kilograms per second times the velocity, meters per second, yeah, we get kilogram meters per second squared, exactly the base units of newtons, right? And so that's another sort of clue, okay, we're just solving for the velocity here in meters per second. So choice C is correct for number 11.